Good evening, everyone. My name is Prakash, and I am from Mechanical Department. So today, I would like to discuss about effect of internal pressure on the dimensions of a thin cylinder. Simply, it is also called as the strains in thin cylinder. So, as we already know, when a fluid having some internal pressure is placed inside the cylinder, due to this internal pressure of the fluid, the stresses are set up at any point of the material in the cylinder. So the stresses developed in these cylinder are, the first one is circumferential stress and the second one is longitudinal stress. So these two stresses are called as principal stresses because these are acting on principal planes. So here, additional stress is also developed in the third principal plane because that stress we are taking as 0 because the thickness of the cylinder is very small. Why? Because actually the third principal stress is radial stress. So here the radial stress is very small for thin cylinders, which is developed at the thickness of the cylinder. So in thin cylinders, the thickness is very small. So that's why this radial stress is neglected. So here we are taking these two, hoop stress and longitudinal stress. So here I am considering the internal pressure of the fluid as P, that is internal pressure. So here L is equal to length of the cylindrical shell. Here I am considering D is equal to diameter of the cylindrical shell, and T is the thickness, and E is equal to Young's modulus for the material, and sigma 1 is hoop stress as we know, PD by 2T, and sigma 2 is equal to longitudinal stress. Its formula for longitudinal stress is PD by 40, and mu is equal to Poisson's ratio, and delta D is equal to change in diameter due to the stresses set up in the material. So here, due to this fluid which is under pressure, the dimensions of the cylinder will change. So here there are three dimensions exist in the cylinder. One is length, another one is diameter, and another one is volume. So due to these two forces, here the length of the diameter changes and the length of the cylinder changes, and also volume of the cylinder changes. So by finding the change in diameter, change in length and change in volume, we can find the strains. So here we are considering E1 is equal to circumferential strain and E2 is equal to longitudinal strain. So as we know, the formula for finding strain in terms of stress is E1 is equal to sigma 1 by E minus Poisson's ratio mu into sigma 2 by E. So as we know, the formula for sigma 1 is PD by 2T. So therefore it can be written as PD by 2T E minus mu into PD by 4TE. Here we are taking PD by 2TE common. So therefore PD by 2TE into 1 minus mu by 2. So this is the formula for circumferential strain. Similarly, we can find out the expression for longitudinal strain. So here the formula for longitudinal strain is E2 is equal to sigma 2 by E minus mu into sigma 1 by E. As we know, the formula for sigma 2 is PD by 4TE minus mu into PD by 2TE. So by taking PD by 2TE common, which remains 1 by 2 minus mu. So this is the formula for or expression for circumferential strain. But we know the circumferential strain is also given as change in circumference due to pressure by original circumference. So this is the generalized formula for strain. So here the change in circumference can be find out by final circumference minus original circumference gives the change in circumference. So here final circumference is, so initially we know the original circumference of the cylinder. The original circumference of the cylinder is pi d. So minus pi d. Here the final circumference is, here the diameter will increase due to the pressure placed in the inside the cylinder. Due to the pressurized fluid inside the cylinder, the diameter will expand. That means the diameter will change. The diameter will increase. So here the final circumference is taken as pi into d plus delta d. So by simplifying this, pi d plus pi delta d minus pi d by pi d. Here these two cancel and pi cancel. We can get delta d by d. So here circumferential strain is also given as delta d by d. So by equating these circumferential strain and also this circumferential strain, we can get, equating these two values, we can get delta d by d is equal to PD by 2TE into 1 minus mu by 2. So this is called as change in diameter by original diameter. So this is called as circumferential strain, delta d by d. If we want change in diameter, delta d is equal to PD square by 2TE into 1 minus mu by 2. So this is the formula for change in diameter. So similarly, the longitudinal strain is also given as change in length due to pressure by original length. Here the change in length is indicated as delta L and original length L. So here E2 is delta L by L. By equating E2, both the equations, we can get delta L by L is equal to what we are getting here, E2 PD by 2T into 1 by 2 minus mu. So here delta L by L is equal to PD by 2TE into 1 by 2 minus mu. So this is the formula for longitudinal strain, that is change in length by original length. If we want change in length, that is equal to delta L is equal to PDL by 2TE 1 by 2 minus mu. So this is the formula for change in length. So similarly, we have to find an expression for volumetric strain. So it is defined as change in volume divided by original volume. So volumetric strain is equal to change in volume by original volume. So here change in volume is equal to final volume minus original volume. So here the original volume we can find it as area of the cylindrical shell into its length. We know area of the cylinder is pi by 4 d square into its length L. So here the final volume can be find out by final volume is equal to final area into final length. So here the final area is pi by 4. Here the diameter should be expanded and length should be expanded in volume. So here the d can be written as d plus delta d whole square into length can be written as L plus delta L. So by simplifying this equation we can get pi by 4 d square L plus 2d L delta d plus delta L d square. So here it is in the form of a plus b whole square, a square plus b square plus 2ab. By multiplying this into this, and we can neglect some smaller quantities, and finally we can get this form. So here it is the final volume. So here by calculating change in volume, so change in volume is final volume minus this final volume minus original volume. Here the final volume is pi by 4 d square L plus 2dl delta d plus delta L d square minus pi by 4 d square L. So by simplifying this we can get, here we can take common as pi by 4. So pi by 4 is taking common, d square L plus 2dl delta d plus delta L d square minus d square L. D square L cancel, and we can get pi by 4 2d L delta d plus delta L d square. So this is change in volume delta V. So here the formula for volumetric strain is delta V by V. So here the delta V is pi by 4 2d L delta d plus delta L d square by volume is pi by 4 d square L. So here by cancelling pi by 4 and pi by 4 and 2d L delta d by d square L plus delta L d square by d square L. Here d square cancel. Here L cancel and d is one time. We can get 2 delta d by d plus delta L by L. So here delta d by d we can written as 2E1 and delta L by L is written as E2. So here the volumetric strain formula is 2E1 plus E2. So if we want, here we know the E1 is 2 into PD by 2TE into 1 minus mu by 2 plus PD by 2TE into 1 by 2 minus mu. So substituting the values of E1 and E2, we can take common as PD by 2TE. So here taking PD by 2TE as common, so here the 2 is multiplied to 1 minus mu by 2, that means 2 minus 2 mu by 2 plus 1 by 2 minus mu. Here 2 cancel and we can get PD by 2TE into 2 plus 1 by 2 minus 2 mu. So by LCM we can get PD by 2TE into 5 by 2 minus 2 mu. So this is the formula for volumetric strain, that is delta V by V. Thank you.